Hey there, Joel here from cosinesound.com.au. Thanks for joining me today. Going to talk about ring modulation and how it works. It's a very interesting synthesizer technique. So many of us know ring modulation by the very particular and interesting sounds that can be created with ring mod, like bell sounds and special effects. So it would be great to do a little video series on this. It can be an interesting technique to use with synths. It's a type of modulation, and there are a couple variations that I'll get into here. And with iZotope Insight, we'll be able to look at some of the finer details of how it works. So there's a passage from Andy Final. He says, "Remember that modulations mean changing something in accordance with something else. In this case, we are changing the amplitude of one signal with another. To do amplitude modulation, we multiply two signals, call them A and B, to get a third signal, C. That can be written simply in the time domain as C equals A multiplied by B." So here I've got two instances of Absynth. I've got the synth outputting a sine wave, and I've got this going into a bus where a ring modulation is applied. So we'll just listen to the original sine wave here, which is 200 Hertz tone, and I'm using an auxiliary so I can also get a meter tap on the spectrogram here. So if I mix in the ring modulation, we'll see two sidebands appear. So now we're just listening to these two frequencies on the ring modulator, which will be 220 plus 80 Hertz, which will be 220 plus 80 Hertz is 300, and then the difference frequency will be the negative frequency, which is 220 minus 80, which would be 140. So that's basically how it works. So ring modulation will give us two frequencies. Now there's a second variation of this which is also quite common, and that's called amplitude modulation. And with this one we'll also get the original carrier frequency come through. That will result once I mix that back in as shown here. So now if I just listen to the output, I'm getting the original frequency plus the sidebands. And in some cases people use this for a particular effect. In general, ring modulation is the more unpredictable sound because it only outputs the sidebands. We don't hear the carrier frequency, and we don't hear the original modulator frequency. In that case, it's also quite rare to be able to listen to the modulator frequency as well. So once again, amplitude modulation gives a modulation of the original carrier signal plus sidebands, and ring modulation gives the multiplication of carrier and modulator with only the sidebands. Now, one of the main uses of AM, or amplitude modulation, we'll just call it AM from now, and RM for ring modulation, is to construct new and more complex spectra by adding sidebands. So if you want to create a particular sound, it helps to know a little bit of the algorithm behind it. Otherwise, ring modulation is pretty experimental effect. So the most common example is a RM sine wave, which creates two sidebands. It's like this. So modulating the sine wave with the sine wave will output 3 frequencies as AM or 2 as RM. Sometimes the AM third frequency is referred to as a DC offset, for example in SynthMaster, and also per data. In other synthesizers like Serum, it's possible to use the modulator oscillator quite freely in this way. Okay, so here's more of an exploration of this ring modulation. So we're listening to 220 Hz with RM. As we lower the RM frequency, the sidebands approach the original frequency. So now it's pretty apparent, that the difference frequency and the sum frequency is not going to deviate very far from 220. So if we set this to 1 Hertz, what we get is 219 Hertz plus 221. And this is the result. Now with amplitude modulation, we'll get a similar result. We get a 1 Hertz beating sound. And I believe that's where the name comes from. It's like a tremolo on the signal, but ring modulation gives only 221 plus 219, and that gives a doubling, a doubling effect or a different summing. As we increase the modulator, the difference partial is going to hit 0 Hertz, and then once it hits 0 Hertz, if we continue to raise the pitch, it will also raise both sidebands. As we said before, for every frequency that comes in, RM creates 2 different frequencies times the number of harmonics in an RM wavetable. So if we have a sine wave with a second partial, we now get 4 partials as ring modulation, and then the third harmonic, we also get 6 partials. But what you notice is that all these partials now have the possibility of overlapping once this modulator frequency is changed. What makes this even more complicated and more unpredictable is that when this modulator has new harmonics, for example, if we add a second partial, now for every harmonic that comes in, there will be 2 frequencies, not just 1, and then we'll have that multiplied by the sum and the difference. So, in other words, 2 times 2 is 4, so we'll get 4 frequencies per harmonic in the original wavetable, as shown here. You can see them crossing over even like this. So how many did we say it was? So we've got 2 here, and we've got 3 here. So that means we should get 4 sum and difference times 3, which should be 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can see here, if we change the pitch, as I just mentioned, we get all these different crossover points. And I can show this from the side view. Let's just go back here. The original sound of the 3 harmonics. Change back to RM. Very interesting tones there. Another way to illustrate this, using 1 harmonic and 10th harmonic, like so. We use the 1st harmonic here and 10th harmonic here. And then we're using 1, 2, 3 here. As you can see, once again, we'll also get a interesting crossover. Although this time we have a very high frequency, which is 10 times higher than the fundamental. You can see here there's the fundamental harmonic on the modulator, and there's the 10th harmonic there. Other techniques that some synthesizers do we can tune the RM to the key, or we can scale it to the key as shown here. And this has to be changed back. We're still listening to that ring modulation there. Now let's mix back in the original carrier frequency, which would be on this tab, and then have AM. There you go, that's just a brief example. There is another kind, which is bright bell sound. So if I open up the bell track I have here, which is actually a organ wavetable, I'll just mix this RM out. Now listen to the organ sound here. Okay, there's an organ sound with a envelope. Now with ring modulation, this is what happens. Again, we lose the original carrier, so we don't really know what the original tuning is. It sounds inharmonic, it sounds more unpredictable and metallic sounding. Especially when we tune way out of the fundamental ranges into 2K. And there you have it. What is the original sound? Quite different. To build on this, we can create more decays, like decaying envelopes, like tuning an offset here, decaying that envelope, tuning this one down a little, decaying that one differently, creating another partial and tuning that one out and decaying that one differently. And then putting it through ring modulation is going to give a very different result. Combining ring mod techniques with similar decaying envelopes can create a richer bell sound. As we notice, when we tune the modulator very close to zero, or at a very low frequency, we get a buzzing sound, and that's because the fundamental frequency has a bunch of fundamental frequencies, you might say, or we get a critical band buzzing sound. So chordal sounds and sub-oscillators, as we mentioned. So RM is a very interesting, simple, and yet diverse tool that comes into synthesis. So I look forward to going into this with more complex modulation sources. Thanks for watching.